Okay, so I wanted to go over the examples that we did today in class, applying our understanding of vectors and components. So here in this first example, we have a box that is suspended from a ceiling, and here's our drawing. It's held up by two ropes that are providing the tension to hold it up, and they are at angles. The first rope is at a 40-degree angle with the ceiling, and the second rope is at a 30-degree angle with the ceiling. Okay, so if we're thinking about problem-solving strategies, the first thing that we are always going to do is draw a free body diagram for our object. Okay, so if we're looking at our mass, our box, we have this, and remember, everything that has mass has an mg going down, and here there's no normal force because this isn't on a it's not on a surface, but it does have two tension forces. There's one tension force going up and to the right, which we call T2. That is at a 30-degree angle. It's important to make sure we note the angles that these things are going at. And then we have T1 going up at an angle, and going up and then making an angle of 40 degrees with the ceiling. Okay, so this doesn't really help us all too much. So after we make to figure out what's going on in our direction, because we like to break our vectors down into x and y, so the second part of our problem solving is we are going to break our vectors into, or sorry, break any vector that is not perfectly horizontal or vertical into its components. Now, when we say we want to break them into their components, like, yeah, it'd be great if we could get a value of these components, but we don't actually know the tension, so we can't get the values, but we do know that for T2, I'm only doing T2 first because that's the one I'm looking at, we have some portion of this T2 that's going up in the y direction, and some portion of it that is going in the x direction. So this would be T2x, and this right here would be T2y. And then we can do the same thing for T1, where we have T1x and T1y. Okay, so I've broken it into its components. Now, what we can do is we can just redraw this Lewis structure. Sorry, I'm in chemistry class. We can redraw this free body diagram to show that we have forces that are acting in the x direction here, which we called T2x. We have a T2y acting as well. We have a T1x, right? So I'm just essentially straight up taking this force and just redrawing it on a new Lewis structure. Okay. Same thing with the T2, just pulling it and pushing it onto a new free body diagram just so that we can see that it is clearly in what we're calling the x and y direction. So we have a T1y, a T2y, we have going in the same direction. We have a T2x going to the right and a T1x going to the left, and then we cannot forget our mg going down. Okay. Now that we have this, our third strategy, and this strategy is for all problems, not specifically this one, but we want to add / net our vectors. So when I'm thinking about this, we think about our x direction and we think about our y direction. Okay, so let's do the x one first. So in our x direction, we have two forces that are acting, and they are acting in opposite directions. So I would just say that the F net in the x direction, F net x, is equal to t1x. I'm just going to follow colors here. So we have this t1x minus t2x. Okay. Now, it doesn't necessarily matter which one you put first or not. Just it is important that you are subtracting them because they're going in opposite directions. It would be, frankly, just as right if you wrote t2x minus t1x. So it really doesn't matter. In general, let's just make sure we define which ways are positive and which ways are negative, just so we have that. So this is our, right, this is adding / netting our vectors in the x direction. We can do the same thing in the y, f net y. And here, I'm going to look at what's happening in our y direction. And in this case, we actually have 3 vectors. 2 of them are going up, 1 of them is going down. So we can say that we have, for the f net, we're going to have t1y plus t2y, and the reason why I'm adding them is because they're going in the same direction, and we are going to subtract mg to get the net force. Okay, so that's step 3, where we're adding and netting our vectors, and then the last thing that we're going to do, right, really the only equation we have been using faithfully this in this unit is Newton's second law. Right, the F equals ma, F net equals ma. Okay, so if I know F net in both x and y, I know that both of these are equal to the mass times the acceleration. Okay, now, most of the time we're looking for the acceleration, but if we're not looking for the acceleration, then we should know something about the acceleration. And right now it doesn't tell us any value for it, but it did give us an important word. It says that this mass is suspended, meaning not moving, meaning the acceleration in the x and the acceleration in the y is both 0. So that helps us down here because we see that if t1x minus t2x is equal to 0, we can set this equation up to say that t1x, oopsies, wrong color, t1x is equal to t2x. Okay, so if I know how to solve for one of them, then I can solve for the second one. And if we come over here, what we can say, again, right, we have t1y plus t2y minus mg is equal to 0. Okay, we can rearrange this again, and we can say t1y plus t2y is equal to mg. So we're just rearranging these equations because they're both equal to 0, right? So when we add these two y components together, they have to equal mg, which we can see this in our diagrams, okay? Now, when we're looking at this, the only thing we actually know in either the x or the y is mg, because we know the mass is 8 kilograms, and we know gravity is 10. So it looks like we have 4 unknowns, okay? But if we go back, I'm going to take our triangle for our 2 tensions and kind of blow them up a little bit. Okay, so say this is T1, and we're talking about T1y and T1x. Okay. Again, we don't actually know what T1 is. That's what the question is asking us for. But if we did, right, we can, or we know how to solve for sides of our triangles. Right now we don't know what T1 is, but we could set up our equation. So T1y is, and when we're looking at this right here, this is the opposite side of what we're calling our 40 degrees. So we would use sine, right? So remember, sine theta is equal to the opposite side over the hypotenuse. Well, in this case, I know that sine 40, the opposite side is T1y, and the hypotenuse is T1. So if I rearrange this equation, I get T1 sine 40 is equal to T1y. And through the same logic here, we could figure out that T1x is equal to T1 times the cosine of 40. And we can do the same thing with our T2 triangle. We'll do it over here. It's going up this way. We would say this is T2, and we have T2y, T2x, and remember our angle over here is 30 degrees, okay? So T1x is the adjacent side again, so this would be T2 cosine of 30. T2y would be T2 sine of 30. Okay. So what we're doing is we're trying to fill in more information of these equations that we have written. And we're also trying to limit the number of unknowns that we have. So T1x, which is in this part of the equation, is the same thing as saying T1 cosine 40, right? We have that written up there, so I can rewrite this, and I can say T1 cosine 40 is equal to, and then T2x is over here, T2 cosine 30. Okay, and then we can do that over here. We have T1y, which we said is T1 sine 40. We can add that to T2y, which is over here, T2 sine 30. And we said that that is going to be equal to mg. Okay, so what we just did here is we eliminated the fact that we had 4 unknowns, and the only unknowns we have right now in these two equations are T1 and T2. Right? Because cosine 40, if you go into your calculator, you can actually get a value for that operation. Okay, so in our calculators, we can do cosine 40, and we get 0.766. And anytime you know the angle, you can do the operation of that angle. So right now we have 2 equations with 2 unknowns, so we can do a system of equations, and we can substitute. So I'm going to, oopsies, my bad. Come over here, and we're going to set up our equation and solve our left equation over here for T1. So we can say, right, T1 is equal to, and we just have to, in order to get T1 by itself, we have to divide by cosine of 40. So we have T2 cosine 30 divided by cosine of 40. Okay. So if we knew what T2 was, we would be able to solve for T1 based on this equation, but we don't. But we have an equation, another one, that relates T1 and T2. So what we can do is we can substitute, and we can take this equation right here, or this part of the equation, and since that is equal to T1, I can plug it in for this. And we can get a new equation that reads, right, so I'm plugging in T2 cos 30 divided by cosine of 40. right? That's T1. And T1 has to be multiplied by sine 40. You can't forget, right? We're only plugging in for T1. We're not plugging in for this entire part of sine 40. So T1, which is in parentheses, multiplied by sine 40. You're going to add T2 sine 30, and that is going to be equal to mg. So now in this equation, right, we have one unknown, which is T2. Because we know mg, and then sine 30, sine 40, cosine 30, cosine 40, these are all values, those are all numbers that we can get. So when we plug into this equation, T2, I'll put in the numbers that we get. So the cosine of 30, we said, was, oh, didn't do that one, we did the cosine of 40. We would do cos of 30, which is 0.866. And I just put this in parentheses up here to remind us that right, this is all in parentheses because that is T1, but this is all multiplication that's happening, so you don't really need to have those parentheses. And we are going to divide by the cosine of 40. Cos 40 is, just trying to keep things straight here. Cosine of 40 is 0.766. That gets multiplied by the sine of 40, which is 0.643. Then all of this gets added to T2, sine 30, which is 0.5. And this all has to be equal to, the mass is 8. Go back up here, right? We have an 8 kilogram mass hanging. 8 times 10, which is 80. Okay, so we can do this math here, and we're going to do 0.866 divided by 0.766 times 0.643. And what we get for the thing that's in parentheses, we get T2 0.727 plus T2 0.5. We're going to say that that is equal to 80. Now we have T2s and we can add them together, so 0.727 plus 0.5, we get T2 1.23 is equal to 80. And now we just have to divide 80 by our 0.123, which is, oopsies, sorry, calculator problems. 1 divided by 65. Okay, so T2 is equal to 65 newtons. Okay, so the tension in this string right here is 65 newtons. Okay. And again, what we did is we substituted in, we got a system of equations, one unknown. Now, what we need to do is solve for T1, which we have an equation here. T2 times the cosine of 30 divided by the cosine of 40 is equal to T1. So let's plug in there to our equation. We get, okay, so T1 is equal to T2, which we said is 65 newtons, times the cosine of 30 divided by cosine of 40. And when we plug, we're going to get 65 You said the cosine of 30 was 0.866, so 65, 0.866 divided by cosine of 40, which is 0.766. So let's do that math. 65 times 0.866 divided by 0.766, and we get a value of T1 equal to 73.5